Welcome everybody to the One World Mathematical Physics seminar, which is run by the International Association of Mathematical Physics. Today's speaker is Holger Gies from Friedrich-Schiller University of Vienna, and he will speak about quantum field theories of relativistic Luttinger fermions. Please, Holger, go ahead.
Oh, thank you very much, Wojtek. Thank you for this kind invitation. It's a great honor for me to contribute to this One World Mathematical Physics seminar. I looked into the program so far, and it has been absolutely impressive, if not for me, intimidating. So this is a seminar at the crossroads of mathematics and physics, I realize, and you will quickly realize that my perspective is that of a physicist. So there's a lot of rigor which still has to be put into this work. But it's also a seminar I realized that is at the crossroads of or draws from solid state physics, statistical physics, and high energy field theory and beyond. And so this talk is also a topic that has been widely known in the condensed matter literature, which we try to transfer to the relativistic case in recent years. So in that sense, I hope I contribute to the spirit of this seminar. So it's about a new toy, which we call relativistic Luttinger fermions, that may help to build interesting models, novel models of relativistic quantum field theories, which may eventually be useful in particle physics applications. But that is still a long way to go, I believed. This is also work done in collaboration with a number of students. I'd like to highlight in particular Marta Pichau, who's at this point in time writing up her thesis, which covers all the material we put out so far. And I decided to give you a longer motivation for why this is of interest to us, why we are looking into such systems. And so let me start with a very generic question. Of course, as physicists, we'd like to write down a perfect theory. So what is a perfect theory? And you may come up with Newton's second law. And in some sense, it's a perfect theory because under minor assumptions for the force, you know when solutions exist and whether they are unique. So there are strong theorems about it. And that's, of course, nice to have. But on the other hand, the equation itself doesn't tell you anything about its validity limits. So it doesn't tell you that it breaks down if you go to large velocities or to small actions where quantum or relativistic effects set in. And I'd like to argue that this is different for quantum field theory. So in some sense, quantum field theories have an additional superpower in the sense that they can predict their own validity scales or their own failure in some sense. So as a maybe not very precise example, but let me mention QED and look at perturbation theory, where the beta function that determines the running of the coupling has this positive sign. And it tells us that if we fix the coupling in the infrared and go to larger and larger scales, then the coupling increases at some point and it actually diverges at a finite scale. So that's a perturbative argument, but let's, for the sake of the argument, assume that the theory itself behaves also non-perturbatively in this way. Then quantum field theory itself, so QED itself, predicts us that there is a maximum validity scale, which is a huge number if you plug in uh, quantitative numbers here. And so that's the Landau pole, the famous Landau pole singularity, which in this line of reasoning tells us there is a maximum validity scale, and beyond you have to go to a different theory. And so you may say this is maybe just an artifact, or it's yeah, far beyond any reasonable scale. But if you go to the standard model, you have such a Landau pole in the hypercharge U1 at much lower scales. If you go to supersymmetric variants or beyond the standard model theories, this maximum validity scale approaches regions which are close to the scale of gravity. So they are used, these arguments are used to constrain physical observables. And for instance, long before the discovery of the Higgs boson, the mass of the Higgs boson, upper and lower bounds have been given by this sort of argument. So this superpower of quantum field theory. And so there are, in fact, theories that can be perfect in that sense, so that are fully controlled. And of course, the prime example is quantum chromodynamics, where the coupling as a function of energy scale decreases. That's the famous feature of asymptotic freedom. And so the control of the theory becomes better and better towards higher and higher energies. And so QCD, quantum chromodynamics, could be a truly perfect theory valid on all scales. And so kind of our motivation is to try to classify those theories that could be truly perfect. And of course, a well-known classification is that of renormalizable quantum field theories. And let's go to the real space-time dimensionality, 3+1 spacetime dimensions. And let's throw in a couple of assumptions, such as Lorentz invariance, locality, and here this community is an expert community on these criteria, locality, and let's say some variant of unitarity, and at least perturbative renormalizability. Then you can classify all possible interactions satisfying these assumptions and a few implicit ones. And it turns out that, for instance, for spinless particles, scalar particles, there's just the 5-4 interaction. For fermions, there is just the Yukawa interaction and the gauge interaction. And for spin 1 particles, there's just the gauge interaction that satisfies these criteria. And it's just an amazing observation that in particle physics, precisely those interactions are made use of in the standard model of elementary particle physics. So that's a great achievement in this line of reasoning. Of course, the graviton is not on this list. There's no theory which we know that satisfies these criteria, and it's obvious we have to go beyond, either beyond this perturbativity assumption or the implicit assumptions that are behind here. But now let's take another look at this table and check whether these theories can be perfect, so ultraviolet high energy complete in the same sense as QCD. And then it depends a bit. So the Yang-Mills interactions, of course, belong to this the list of perfect theories. And for all the other interactions, it depends. It depends on the precise content of the theory. They can, may or may not be, depending on the details. So for us, a motivation is, well, is this all there is? And can we go beyond? And what about these implicit assumptions of the perturbativity assumption? So let me, as a next step, try to say a bit about these implicit assumptions. Of course, we can give up perturbative renormalizability. And the way to go in that direction would be asymptotic safety. So that means the coupling, as in QCD, does not need to necessarily approach a zero value towards high energy, but it could also approach a fixed point value, a finite value. The theory could be interacting, but develop quantum scale symmetry, and that could give rise to a non-perturbative ultraviolet, well-controlled limit in some sense. We could also talk about boundary conditions, which are implicitly assumed for these generating functions, but that's not the topic of today's talk. What is also behind this list of classifying theories is conventional canonical scaling. And the way to go beyond is what is called higher derivative theories. And in some sense, what I would like to present today also belongs to these higher derivative theories, but maybe a bit different from what is usually discussed. So let me explain very briefly and very elementary canonical scaling. Let's focus on Dirac's theory. So this is the conventional relativistic Dirac action, the kinetic term, the Dirac spinor, the spin structure in terms of the gamma matrices, and it's linear in the derivatives. And if you now count engineering dimensions, then the derivative comes with mass dimension 1, the volume with mass dimension -4 in 3+1 dimensions, and the action should be dimensionless, which tells us that the spinors carry mass dimension 3.5. And that immediately tells us that a self-interaction, here of this Korsner-Voigt type, psi bar psi squared, so a 5-4 type interaction for fermions, that requires the coupling to carry an inverse mass dimension, which is beyond the criteria for perturbative renormalizability. So the immediate conclusion is, in 4 dimensions, this interaction has to be ruled out. It was not on the list that I showed you. Actually, if you change space-time dimensionality, if you go to 1+1 dimensions, then it's well known, well studied, that this interaction has exactly mass dimension 2, which means the coupling of this Gauss-Neveu type is dimensionless, and that belongs to the class of perturbatively renormalizable coupling. And in fact, it's an asymptotically free theory. It's a perfect theory in that sense that I presented you. And in fact, here, there are truly rigorous results, starting with the work of Kawecki-Kupian in the 80s. Feldman has contributed a lot, and then rigorous proofs by Christoph Kopper and Manfred Salmhofer and collaborators. So here it has been established that this theory is perfect in the sense that it's constructible in the ultraviolet rigorously. Now, the question I'd like to address is this one: is there life beyond conventional canonical scaling along the line of arguments that I gave you so far? And the answer is obviously yes. And this is well known from statistical physics, if you go to interacting with the systems with interacting fixed points like ON models in 3 dimensions, if you have critical phenomena, or in particle physics we call it asymptotic safety, then you can have large anomalous dimensions, and that of course modify the power counting, modify the way the loops and the propagators contribute, and theories can be truly perfect in that sense of approaching fixed points in the ultraviolet. But if you ask for the recoupling regime, then the answer is typically no, and the argument is, well, there's Weinberg's theorem that tells us in power counting, perturbatively, you only receive logarithmic modifications, and that doesn't help to make diagrams better behaved in some sense. So the standard answer is no, and even more so if you just by hand kill the standard kinetic terms and put higher derivative terms, the standard kinetic terms are typically unstable against fluctuations, and so the standard kinetic terms are generated, and you're back to conventional power counting. Unless you put an extra symmetry. And so here is an inspiration from solid state physics that gave rise to the ideas I would like to present to you. It goes back to work by Luttinger in the 50s, and he was interested in semiconductors in a magnetic field. And he had spinorial degrees of freedom. Actually, this wave function here, you should think of it as a quantum mechanical wave function, has 4 components, so he has 4 bands in his system. And he was interested in writing down the most general Hamiltonian, which is rotationally invariant in a more general sense. So you can rotate your vectors, but at the same time, he allowed for a mixing of these 4 bands. So by rotation in space, he allowed also to mix these bands. And so the most general form of the Hamiltonian is not just the Laplacian squared. It's a mixture of the spatial indices with the spin structure. So these GIJs, they carry spacetime indices or space indices, but they also carry internal spin indices corresponding to the 4 bands. And so these matrices here, they have to satisfy an algebra, which nowadays is called the Abrikosov algebra, because Abrikosov in the 70s rediscovered this idea again and generalized it. And so it's a Clifford type algebra, an anti-commutator for these matrices. And on the right-hand side, you essentially have an identity in spin space and some prefactors to saturate the indices. And so this structure is nowadays used for so-called quadratic band-touching materials or band-crossing points, in the sense that you may have bands which do not just cross, but which touch each other quadratically. And so there are a wide variety of systems where this is nowadays applied, cycloiridates and even pneumatic quantum criticality systems. And I learned about this from Lukas Jansen and Igor Herbert 10 years back. And so I was interested in the simple question, well, can this be generalized to relativistic theories? Because here you see this is Lagrangian, which is linear in time or Euclidean time here. So it's a non-relativistic theory. And I was asking myself, well, can this structure be transferred to the relativistic case? But before I come to this, let me try to give you a feel for this Abrikosov algebra. So let's compare it side to side with the Dirac case. So in the Dirac case, let's go to 2 dimensions to be very explicit here. We may write down a Euclidean 2-dimensional Dirac algebra with 2 gamma matrices, which can be represented just by the Pauli matrices. And then the Dirac operator is linear in the derivative. And so in spin space, the Dirac operator is a matrix, and each component is linear in the derivatives. Now, this Abrikosov algebra can also be represented. It now contains more elements, but still the elements can be represented by just the Pauli matrices. And the Luttinger operator is quadratic in the derivatives, so each component of this Luttinger operator in spin space is quadratic in the derivatives. So in that sense, it's a higher derivative operator compared to the Dirac case. And so the obvious question is, can you make this relativistic? And of course, it's very straightforward to write down the Abrikosov algebra relativistically. You just replace the indices by Greek indices and replace the Kronecker deltas by metric factors on the right-hand side. And then you put your favorite metric, and that looks already pretty relativistic. But of course, I don't just need the algebra, but I want to write down a kinetic action. And so it kind of looks trivial. I use this operator, I sandwich it by spinors, now for fermions, psi bar psi. But the question to be addressed is, what is psi bar? Because you want to have an action that satisfies, of course, certain criteria. You want to have a real action that has the chance to lead to a unitary theory. And so the question is, what is psi bar? And in the Dirac case, there is a simple answer. There is a spin metric which combines the conjugate, which allows you to construct the so-called Dirac conjugate, which in the end establishes relativistic invariance. And so here we have a lot of, of these G matrices that may play the role of this gamma naught. So what is the spin metric? And already from the condensed matter literature, it was clear that if you can also do the condensed matter construction for space dimensions. And it was already known that this may lead to problems because you end up with spinless fermions in that case. Before I tell you the answer, let me try to give you a feel for this Abrikosov algebra. It's now a bit technical, but it may be worthwhile to just get a handle on this, how to view these matrices. So these G mu nu for each fixed index spacetime index mu and nu from 0 to d minus 1 is a d gamma by d gamma matrix, and it's a priori unclear what the d gamma has to be. But of course, since it's contracted with partial derivatives, we know it's symmetric in these Lorentz indices. And we also choose them to be traceless in the Lorentz sense, because if it had a trace, the kinetic term would just correspond to the Klein-Gordon operator, which is not so interesting. It also would violate some of the symmetries we are later interested on. But so let's just for simplicity exclude this trace. And then you can just count the number of independent matrices that you need in order to satisfy this Abrikosov algebra. And it turns out that the number of independent elements goes with the number of spacetime dimensions squared. So it grows much stronger than in the Dirac case, where the number of elements that you need is just the dimensionality. You need gamma 0, gamma 1, gamma 2, gamma 3 for 3 plus 1 dimensions for the Dirac theory. And then the gamma, so the size of the matrices that you need in order to represent this algebra goes like 2 to the power of the number of elements divided by 2. So it grows rather strongly with the dimensionality. So let's be specific. In 2 dimensions, as I showed you already, I need just 2 elements. I can represent them by Pauli matrices, which are 2-dimensional. But in 3 plus 1 dimensions, for spacetime dimensions, I need 9 elements. And so I need a 16-dimensional representation of these matrices at least. And this number grows very fast. So if you go to 6 spacetime dimensions, the matrices become very, very big, and it also means the spinors become very big. again, you don't have to look at the details, but just to convince you that these algebra can be realized non-trivially, let us start with a Euclidean Dirac algebra, and then you can construct these matrices from linear combinations of these Euclidean algebras, and you have to put certain prefactors here in front of the Euclidean gamma matrices, and you need up to 9 of them, and then this set of G matrices satisfies the upper course of algebra in the relativistic case. And of course, there are many other representations that are all connected by spin-based transformations. Okay, so now let's come back to this puzzling question. What is the conjugate spinor which we need in order to construct a real action? And so let's make an ansatz. Let's put a spin metric. And in the Dirac case, the spin metric is just the gamma naught matrix. But now the requirement that the action should be real for the Luttinger case now imposes certain commutation, anti-commutation relations of the spin metric with the G matrices. And it turns out there is no solution for the D gamma equals 16-dimensional representation. But of course, you can use high-dimensional representations. And the lowest, in our sense, irreducible representation where we can maintain Lorentz symmetry is the D gamma equals 32-dimensional representation. And so that's also the size of your spinor. So the degrees of freedom that we will write down in our field theories will have lots of components. But then with this explicit form of the spin metric, and there's yet another one we could choose, we can prove that the action we wrote down is Lorentz invariant because the Lorentz group turns out to be a subgroup of this spin base symmetry as it is in the Dirac case. And you can follow the proofs for the Dirac theory to show that bilinears formed from this G matrix, they transform like tensors under Lorentz transformations lambda. Okay, so we do have a relativistic theory. We know how to transform the fermions. We know how to transform the G matrices. And so the theory is Lorentz invariant, and it is also spin-base invariant under a huge group SL32C. But now we are back at the beginning. If we now do canonical power counting, it turns out that these fermions have canonical mass dimension 1. And that's just like a scalar field 3 plus 1 dimension. And that means the phi-4 theory, which is marginal, is also marginal in this case. So a psi bar psi squared, a Gross-Neveu type interaction, is perturbatively RG marginal, and so could be among those that are renormalizable and maybe even perfect if asymptotically free. In fact, this is just one example of a bilinear which I can square to get interaction. I can count the number of bilinears, and since I have such huge spinors, so 32 component spinors, I can count up to 1024 independent bilinears, and this should be compared to only 16 for the Dirac fermions. So there's a huge space of possibilities of possible interactions which can be explored. We just have explored a couple of them so far. Now, let's try to generalize this. So far, we just had a kinetic term. Let's try to put a mass term. And here, this would be, the naive version of a mass term. You could add just a bilinear in this psi bar psi. And of course, you can write down the equation of motion. So this is the relativistic Luttinger equation that in momentum space that you could compare to a Dirac equation. And by the same tricks that you use for the Dirac equation, you can show that each component of the spinor has to satisfy this equation here, p to the 4 minus m to the 4, which you can factorize into a standard Klein-Gordon equation with a nice mass term. But then you get a factor, and of course, the experts among you who thought about high derivative theories might have expected so. You get a kind of wrong sign Klein-Gordon equation. So you get what is called a tachyonic mode. And as I said, this should have been expected from the very beginning. And let me open here a parenthesis. Let me compare this to a higher derivative scalar theory. So I start with a scalar theory and add a Laplacian squared as kinetic term here. I put a corresponding mass term, and then the propagator can be decomposed in a partial fraction decomposition, and you get a standard scalar propagator, but in addition, you get a tachyonic propagator and you get a negative residue. So which is it's a negative norm state in the sense of a spectral representation of Lehmann-Thiele. And so in addition, you have this tachyon, which indicates instability, and you also have what is called a ghost state. So this conclusion need not, so it's not, automatic. So for instance, there are examples, high derivative theories, for instance, stellar gravity, where you may have ghosts, but you do not necessarily have to have tachyons. So it's not as immediate as it may seem from Ostogatsky's theorem. So as I said, this was just a parenthesis. Let me now go back to the Luttinger relativistic Luttinger case. So far I discussed for you this naive mass term, but the point is, since we have a further gamma structure, so like in the Dirac case, you have a gamma 5. Here we have two sorts of gamma 5 matrices, namely the gamma 10 and gamma 11, because we have to go to this 32 component representation. And there's yet another product of gamma 10 and gamma 11, which helps us to write down four different mass terms. And that's a bit similar to those of you who know about 2 plus 1 dimensional Dirac materials. There are also two possible mass terms, the standard one and the so-called Haldane mass. And here, these terms here are similar to these Haldane masses. And in the following, I will concentrate on this gamma 11 type mass term, with M11 mass. And if I use this mass term, I can go through the same arguments as before for the naive mass term. It turns out that now each component satisfies this sort of equation in momentum space. So that means that the spectrum for this operator is really gapped and there's no tachyonic mode. That's actually also similar for this other mass term here. Let's now take all these bilinears, psi, psi gamma 10, psi gamma 11, and so on, and let's form interactions. So far I just discussed the kinetic term, possible mass terms. Some of them are nice, some of them are badly behaving. And now let's form interactions out of them. Now I switch on interactions, and each comes with a coupling lambda. And now you can use your favorite method to do perturbative field theory, Feynman diagrams, or whatnot. I will be using the functional RG, the Wetterich equation, because it generalizes to also non-perturbative applications, which I will show you later on. But at this point in time, it doesn't matter. Just do perturbation theory. And within perturbation theory, you can compute the running of these couplings whenever you put one of these interactions. And I show you here the simple result in the large N limit. So where NF is the number of different flavors which are put for the Luttinger fermions. And in the large NF limit, all these beta functions simplify to this result. We also have results beyond large N, but let me just show you the simple formulas. So the nice thing and the important point here is that the beta function for this coupling is negative. So it's like in QCD, which means all these theories, independently of which one of you put, is asymptotically free at high energies. So this is, to my knowledge, the first set of purely fermionic matter models that is asymptotically free without having a gauge interaction. If you worry about this large NF limit, the true expansion parameter is actually 1 over d gamma by NF, and d gamma is 32, which means even for one flavor, we are already pretty close to the large NF limit. Okay, so keep in mind, Luttinger fermionic models allow for asymptotically free interaction, and in my classification, they are candidates for perfect, ultraviolet, complete high energy complete quantum field theories. But of course, once you have an asymptotically free coupling, you worry about what happens at low energies, because then the coupling grows strong. It's like in QCD, things become difficult, right? And so in these models are much simpler than QCD. There are certain tricks which we can play. So here I concentrate on this gamma 11 model. You see the psi bar gamma 11 interaction squared, and this coupling, which we know is asymptotically free. And we can introduce an auxiliary field, a Hubbard-Stoyanovich field it's called. So we can linearize this theory, or bilinearize this interaction in terms of an auxiliary field, such that this purely fermionic action is equivalent to this Yukawa theory, where I have a scalar mass term and a Yukawa coupling between the scalar and the fermions, provided that this original coupling is connected to the mass term and this Yukawa coupling by such a matching condition. And then we can solve, at least to mean field level, the effective this theory and compute the effective potential for this scalar field. And it turns out that the result is a very nice one. So this is the effective potential now for this scalar field, and you see it has a nice minimum here. And it has a typical Coleman-Weinberg type shape, so phi squared log phi squared. And so this theory in the strong coupling regime is symmetry breaking, so it exhibits a vacuum expectational value. It has a stable minimum. There are no imaginary parts appearing here, so no instability in the sense you would have or might expect from the Ostogatsky type instability. It's a prime example for what Coleman called dimensional transmutation, because in the end, the scale of this minimum sets the scale for all quantities. And we can work out the low energy spectrum. So there's a scalar excitation here, which has a mass because of the curvature, and the fermion spectrum is gapped. And so that's the low energy behavior. And in the ultraviolet, you have asymptotic freedom. So it's very similar to the Gauss-Neveu model in 2 dimensions. Now let me go one step further, and that's now, when you look at the results, a qualitatively decisive step. So let me make this auxiliary field, this Hubbard-Stoyanovich field, which I introduced, the scalar field, let me make it dynamic by putting an additional kinetic term and an additional potential that you may write in terms of a mass term, a cell interaction, and so on and so forth. So if you look at this Luttinger Yukawa model, you observe that from a perturbative viewpoint, you observe there are 3 parameters: Yukawa coupling, mass term, scalar self interaction, which you would classify as either RG relevant or RG marginal. So in total, you expect 3 physical parameters. But since 2 of these parameters are RG relevant, you expect that in order to separate a possible high energy scale, way to fix the theory, from the low energy physical masses, say, the physical spectrum, you expect that you have to fine-tune the initial conditions for these parameters very precisely. So that is exactly the heart of the naturalness of fine-tuning problem in the standard model, in order to separate the Fermi scale, Higgs mass, top mass, etc., from a possible underlying high energy scale, say the Planck scale. You have to tune the Higgs mass parameter potential to a very high degree. And so, the same thing you expect here, that you expect that there are 3 physical parameters. But it turns out that actually, if you compute the flow of these running couplings, in particular the Yukawa coupling and the phi-4 coupling, so here's the phi-4 and here's the Yukawa, turns out that in this plane of couplings, there is what we call a pseudo fixed point, a partial fixed point. So it doesn't really matter where you start, where you initialize your flow at a high scale. You always run towards this fixed point very quickly, and you stay there for a long time. The only non-trivial bit is the scalar mass parameter, so this mass parameter here, but instead of being relevant as it is in the standard model, it turns out to become marginal when the other couplings are at the fixed point. And so this coupling here runs very slowly. It runs logarithmically slowly towards negative values. So the system, independently of where you start, approaches this fixed point quickly, and then there is a slow residual running towards the symmetry breaking regime. And so it's absolutely natural that the infrared parameters, scalar mass, fermion gap, is far separated from a possible high energy scale. And we dare to compare this to what people in statistical physics call self-organized criticality. So it's like the famous Bartang-Wiesenfeld sand pile model. In our case, there is this partial fixed point. All the couplings, also possible high order ones, they are controlled by this partial fixed point. Then in the sand puddle model, what is the dynamical time where you start dripping sand is in our case the RG time. And in this sand pile model, what after a while, so that the sand piles up and independently of where you put the sand, at some point you kick off avalanches, and these avalanches have a typical critical behavior, which can be characterized by exponents. In our case, so the critical behavior is that the scalar potential becomes symmetry breaking, and we have mass generation, etc. And in our case, this slow driving force, which in the sine pile model is this slow dripping of sand, is in our case this running of a scalar mass parameter. And that implies that large hierarchies can be absolutely natural. Now, there's no fine-tuned fixing of initial parameters necessary here. And so, since it's important, let me compare this to the Dirac case. So in the Dirac-Yukawa theory, which you can think of as the electroweak, the top Higgs sector of the standard model, where you also have Yukawa coupling, a scalar mass parameter self-interaction. You do have three parameters. You do need three observables to fix these parameters. For instance, you need the Higgs mass is an observable. You can't predict it. Top mass is an observable. The vacuum expectation value is an observable. But in our case of the Luttinger Yukawa system, we only have three. We do have three parameters, but we have these two fixed by the partial fixed point condition, which means we only need to fix one observable, which is just a scale. So we fix, say, the analog of the Fermi scale. And then both the corresponding scalar mass and the fermionic gap, they are a prediction. And for instance, their ratio, we predict it to be this particular number here. And here this ratio is plotted as a function of the flavor number. And you can see here this is a very small, it's 0.78 to 0.79. Already the NF equals 1 case is already very close to the large NF limit, as expected. Yeah, so this is this very unusual feature of self-organized criticality present in these Luttinger systems. Now, I told you about the nice and good things: asymptotic freedom, possibly perfect theories, self-organized criticality, no fine-tuning. Let me also talk about the problematic aspects. And I already mentioned, if I add a naive mass term, there is a tachyon in the spectrum, or can be a tachyon in the spectrum. In fact, if I look at the energetic structure of the propagator in Minkowski space, then, and I do partial fraction decomposition, then my propagator has 16 components which behave like a Klein-Gordon propagator. And I've 16 components which behave like a ghost, so a negative residue, and a tachyonic mass. So that theories with these properties are probably unstable. And in fact, we used also the Gauss-Neveu type interaction, studied it and found it to be unstable. So it's just like you expected. If you put in something which is sick from the beginning, and a theory that contains tachyons is in some sense sick from the beginning, then also the results you derive from it show these instabilities. But we can do the same analysis for these four different mass terms. And so I summarized this here. So the naive mass, which I just showed you, has this tachyon pole in the complex p squared plane. That's the sig part, the instability. But for instance, for the gamma 10 mass, there is not a pole, there's a branch cut. And for the gamma 11 mass, there's a branch cut along the imaginary axis. This was the type of theories which we also studied in an in the interacting case. So we have this branch cut along the imaginary direction. And if we use this other mass, we get poles in the complex plane. And so what this tells us is that we don't have a spectral representation in the Lehmann-Chalane sense for all these systems here. And yeah, but for specifically these gamma 11, gamma 10 models, so the lower bit here, where the structure is along the imaginary direction, there are no tachyons. We find these complex conjugate poles or branch cuts, which is very similar to what Gribov and Stingel have hypothesized in the case of low energy QCD. So that was at the time a model for how QCD in the end expresses the confinement of quarks and gluons in certain gauges in the complex plane for the propagators. So there is no spectral representation in this Lehmann-Chalane sense, and therefore there's also presumably no LSZ type construction of an S matrix. So for me, the conclusion at this point is that for these models here, probably the Luttinger fermions are not asymptotic states. They might be useful internal states that you can use to for quantization inside loops in the perturbative sense, but you shouldn't try to compute S matrix elements because you don't know how to write down an S matrix in the first place. So that, maybe I changed the color of my laser pointer here. That, of course, means there are a lot of red flags. Since there's no spectral representation, we can't make statements about the positivity of the state space at this point in time. You may worry about applicability of standard theorems like spin statistic or CPT. And the way I understand it at this point in time is that I think we shouldn't think of the relativistic Luttinger fermions. We shouldn't think of them as asymptotic states. And if they are not, then there's a simple possible cure for these theories. You may combine them with non-abelian gauge theories, because if they play the role of quarks, then non-abelian gauge theories confine them kind of automatically if the gauge theory has a suitable number of colors. And in this way, you anyway wouldn't expect these Luttinger quarks to be asymptotic states. Okay, so this brings me more or less to the end of my talk. This slide is rather meant as a joke, but I'd like to make it just as an inspiration. Don't take it too seriously. But you may wonder about what to do with these large number of components in your fermion, right? So it's a 32 component object. But 32 is not an unusual number if you look at the standard model. So if you consider one standard model family, you have up-type quarks, which come in three colors. You have down-type quarks, which come in three colors. You have an electron, which is one Dirac fermion. And if you add also right-handed neutrino components, this would also correspond to one Dirac fermion. And so if you sum it up, one family in the standard model has 8 Dirac fermions, which makes 32 components, right? So it's as I said, numerology, don't take it too seriously, but it can be inspiring. Very good. So let me come to my conclusion. I hope I convinced you that there is this new toy, Luttinger fermions, in relativistic one of these theories in 3+1 spacetime dimensions. And you can write down theories that have full Lorentz symmetry and have full spin base symmetry, which is a huge symmetry, SL32C. And you can use them as building blocks for power counting renormalizable theories, which can be ultraviolet complete and asymptotically free. And as a particular bonus, which we didn't expect before, and they can have features like self-organized criticality, so that you have natural scale separation without the need of fine-tuning. there's a huge set of interactions that you possibly can study, and as I showed you the number of bilinears that you can write down. And so we haven't explored them, of course, in depth so far, but there's a lot of work to be done. But of course, there are a lot of questions in particular concerning the red flags, which I mentioned, and you may have many more questions at this point. Thank you.
Well, thank you very much for this interesting talk. Are there any questions or remarks? Okay, yes. Please just unmute yourself and ask.
Okay, it's me, Erhard. My question is just for the free Luttinger fermions with one of your preferred mass terms. Are they ghosts or not?
Yeah, thank you. This is kind of visible here. Um, for this particular mass, there are complex poles, and once there is a pole, you can determine the residue. And so this pole has a residue -1, so there is a ghost. For the case of a branch cut, I can't define a residue, so I can't answer your question. But here there is a ghost.
No, but I mean, in the free case, there should be something like a Hilbert space or maybe what's called never linear space, potentially something that has both positive and negative norms. But that has not been done yet, or what?
No, so we look at it from the Lagrangian viewpoint, and this is all you get from that. So at the moment, we are also looking at it, in a Hamiltonian quantization. So this is
Yes.
work going on with Yunsin Yi, and we have some preliminary results, and it seems that we can at least define a subset of the Hilbert space which doesn't contain ghosts. So, and that subset seems to, I mean, this is all preliminary, seems to correspond to those states which we integrate over in our quantum field theory. So, in the field theories we studied, so this Yukawa theory, for instance, we always integrate over, so we have scalars as external states, and the fermions always occur in the loops. And so these loops, there's charge conservation for these loops. And those states which we combine seem to be those that don't correspond to the ghost set of states that could be around in the Hamiltonian quantization.
Well, it's
No, but
certainly an extremely interesting structure, but I think this problem of unitarity has to be analyzed.
I fully agree. Yeah, so
Yeah,
I
but
fully
thank you. I
subscribe to
mean, you
this.
made it very clear what has been done and what, and the models are interesting just as models, no doubt about that. So thank you.
Thank you.
So any other questions?
Yes. So
Yeah.
you discussed at least 4 different kinds of mass terms, but do you have a sort of complete classification of possible masses?
Yes, so this is a complete classification because, of course,
Okay.
the mass should be a Lorentz scalar, right?
Mm-hmm.
And so these are the only scalar bilinears we can write down.
Okay.
The gamma 1 to gamma 9,
Mm-hmm. Mm-hmm.
they belong to the G mu news. So
Mm-hmm.
if we would use them, they would lead to Lorentz tensors, but not scalars. And so we have these additional 2 gamma 5 type matrices, gamma 10 and gamma 11, and the product, which you can use for these scalars. Yeah. So that's a complete list.
Okay. So as for the mass term, you have complete list, and you said that as for interaction, you still have many things which are
Yeah,
not considered yet.
right. So we have
Mhm.
1024 bilinears.
Okay.
If you boil that down to Lorentz invariants, it's a
Yes.
couple of hundreds. So we
Uh-huh.
have a classification, but it's it's a
So
lot.
yeah, but probably AI can help you on that kind of thing. Uh-huh. Well, yeah, thank you. That's very interesting.
So maybe let me ask, could you say a few words about this mean field case, which is asymptotically free? What is exactly meant by taking the mean field limit of this model?
Okay, so these are two different things. Sorry. Yeah. So these are, let's say, self-interacting fermionic models, right? And each of one of them is asymptotically free in the large NF limit, and also actually beyond.
Okay.
So that is that this we prove, but you can prove perturbation theory, straightforward perturbation theory, and this is the result. When it comes to the infrared, you have to use further tools. You just know in that fermionic language that the coupling grows strong, so you have to go beyond. And the mean field technique, the Hubbard-Stratonovich transformation, is the simplest, let's say, method you can use. It's exact in the large N limit, NF limit. And if we want to go beyond the large NF limit, you can either do an expansion or you can use this functional RG computation. And then our computation, so these results, which I showed you, they are results in a systematic derivative expansion of the effective action to next to leading order, or next to leading order. And so it's close to mean field. Mean field gives us the zeros order, and at higher orders we get contributions from the bosonic fluctuations. Order parameter fluctuations.
Okay, thanks. Any other questions?
Yeah, can you explain something about how do you calculate this asymptotic freeness? So do you do like usual perturbative expansion beta function and something like that? Yes.
So you take any of these interactions, and then this defines a vertex.
Yes.
And so in order to get this result, you just need the one loop diagram, which is essentially this one. And it suffices to compute it in the zero momentum limit. And that's exactly this result. So you just open your favorite book on quantum field theory, do a perturbative computation of this diagram, and you get the beta function.
But your propagator is something strange, but still.
Yes. And right. And if I use the mass terms of this type, then this loop wouldn't be defined properly. But of course, for the beta function, you can go into what is called the deep Euclidean region, and then the masses don't matter.
Yes.
But for these type mass terms, the loop is also infrared finite.
Okay.
Okay. Any other questions? If not, then maybe let's thank the speaker again. And
Thank you very much.
stop the recording.